Welcome to lecture 48. This is week 10 and we are talking about nonlinear constant programming problems. So, constrained nonlinear programming problems. In our previous two lectures, we have talked about successive linear programming method and successive quadratic programming approximation method. So, in those methods, either we used a linear approximation of the problem, general nonlinear problem, or we made use of quadratic approximation of the general nonlinear programming problem and solved it. We have seen that both linear programming problem and quadratic programming problem can be solved efficiently and reliably. So, in case of successive linear programming problem and successive quadratic approximation problem, the nonlinear programming problem could have been solved efficiently. So, in today's lecture and the following lecture, we will see other class of methods known as transformation methods. So, today we will see penalty function method. So, we will see penalty function method, which is a transformation method, and in the following lecture we will learn about augmented Lagrange multiplier method, which is another transformation method. These transformation methods convert the original constant problem to a sequence of unconstrained problems. So, as the name suggests, the transformation problem will transform the original constant problem to a sequence of unconstrained problem, and we have already seen that the unconstant problems can also be solved very efficiently and reliably. The motivation for the transformation method is that we can solve the constant optimization problem using algorithms for unconstant problems, which can be solved efficiently and reliably. In penalty function method, the constant problem is transformed into a sequence of unconstant problems by adding penalty terms for each constant violation. So, we add penalty terms for each constant violation in case of penalty method, and that way we convert or transform a general nonlinear programming problem into a sequence of unconstant problems. Penalty function methods are classified depending on how they handle inequality constants. All transformation methods treat equality constant more or less in a similar way. So, the way equality constants are handled is similar in almost all methods that come under transformation methods or penalty methods. The penalty function methods are classified depending on how they handle inequality constants, because the handling of inequality constants are different for different penalty function method, but for equality constants it is more or less similar. Let us consider x t equal to 1, 2, 3, 4 etcetera approximate the stationary points of the sequence of associated unconstant problems. We stated that a general nonlinear programming problem will be converted to a sequence of unconstrained problem by use of penalty function approach. So, we consider x 1, x 2, x 3, x 4 are the stationary points for the sequence of these unconstrained problem. Now, if this sequence contains feasible points, we call this method as interior point methods. Such methods are also known as barrier methods. If the sequence contains infeasible points, we call the penalty function method as exterior point methods. So, there are broadly two types of methods, interior point methods and exterior point methods. In case of interior point methods, the stationary points of the sequence of the unconstant problems will be feasible points. We also call these methods as barrier methods. In case of exterior methods, the stationary points for the sequence of unconstant problems will contain infeasible points. So, interior points always contains interior point methods always contains feasible points as the stationary points for the unconstant problems, but exterior point methods will contain infeasible points as stationary points for the associated unconstant problems. As we stated, the penalty function method solves a nonlinear programming problem by transforming a constant problem into a sequence of unconstant problem. Let us consider a general nonlinear programming problem. So, you have minimization of function f x, where x is n vector and subject to p number of inequality constant g x less or equal to 0 type and m number of equality constants h k x equal to 0, k equal to 1 to m. Now, this nonlinear programming problem can be converted to an unconstant problem by adding penalty. So, what we do is the penalty function is defined as the objective function plus a penalty term. This is known as penalty function. So, penalty function is nothing but the objective function of the original nonlinear programming problem plus a penalty term. So, the penalty term is the function of a penalty parameter r and all the constants that the original nonlinear programming problem will have. So, the penalty term is a function of a penalty term r, inequality constant g x, equality constant h x. So, penalty function becomes a function of the decision variables and the penalty parameter, because the objective function, the inequality constants as well as the equality constants are all functions of decision variables x. So, the penalty function can be formulated as sum of objective function plus one penalty term. The penalty term is a function of the constraints as well as a penalty parameter. Note that the penalty function is now an unconstant problem. So, after the penalty function is formulated, the unconstant penalty function can be minimized for a series of values of the penalty term r. So, we can take various values of r and can solve a sequence of unconstant problems, and you will get the sequence of minima to approach the minima of the original constraint problem. So, after you formulate this penalty function for the original nonlinear programming problem, you solve this penalty function starting with one value of penalty term r. So, you minimize this unconstant function using any standard numerical methods for minimization. Some of those methods we have discussed already. Now, you again change the value of r and solve the next sequence of unconstant problem. If we go on doing like this, we will see the sequence of minima that we get will approach to the optimum of the original constant nonlinear programming problem. The penalty function method solves a nonlinear programming problem by transforming a constant problem into a sequence of unconstant problems. Each time we modify a set of penalty parameters and start a sequence with the solution obtained in the previous sequence. At any sequence, we solve this unconstant problem. Let us say we are solving for a minimization problem. This unconstant minimization problem can be efficiently solved using any method for unconstant minimization. Normally, for practical problems, analytical solution may not be applicable and you must make use of the numerical methods for solutions of this unconstant problem. And there are a host of powerful unconstant minimization techniques which can solve this problem very efficiently and reliably. Now, let us talk about different types of penalty terms. Different penalty terms are used for equality and inequality constants. For equality constants, the penalty term that we use is known as parabolic penalty. So, the parabolic penalty term is nothing but the penalty parameter r into square of h. H is the equality constant. So, the parabolic penalty term for equality constant is r into h of x square. The feasible points always satisfy h x equal to 0. Any infeasible point is penalized by an amount proportionate to the square of constant violation. Note that any h x that is not equal to 0 is a violation of the constant. So, any infeasible point is penalized by an amount that is proportional to the square of constant violation. The extent of penalty is controlled by the penalty parameter r. By changing different values of r, you can control the extent of the penalty. Initially, a small value of the penalty parameter r is used and then it is increased gradually as iterations proceeds. Since all infeasible points are penalized by parabolic penalty for equality constants, this penalty is an exterior penalty term. Next, we talk about infinite barrier penalty. Infinite barrier penalty is for inequality constants, and this is defined as r into absolute value of the inequality constant. If you have more than one inequality constant, you have to sum them up. but you will take or you will consider only for the violated constants. So, note that the infinite barrier penalty term is defined as R into sigma g j of x, where j belongs to j bar, which represents the set of violated constants at the current point. So, basically you adapt the constant violations. Here the penalty parameter R is a very large numbers, say 10 to the power 20 or so. Thus, a penalty proportionate to the constant violation is added to the objective function. Since all infeasible points are penalized, this is also an exterior penalty term. Next, we will discuss is log penalty for inequality constants. Log penalty for inequality constant is defined as R ln minus g of x. Note that for infeasible points, g of x is greater than 0. Thus, this penalty cannot assign a penalty to infeasible points. More penalty is added to the points that are close to the constant boundary, that means points with very small g x. Here we start with large values of R and then gradually reduce the value of R. Since all feasible points are penalized, this is an interior penalty term. Note that log penalty for inequality constants is an interior penalty term, because here all feasible points are penalized. Bracket operators handles both constants, which is defined as max 0 g x. So, the maximum value of 0 or g x. The bracket operator is mostly used to handle inequality constants. Here we start with a small value of R and then gradually increase the value of R. Since all infeasible points are penalized, this is also an exterior penalty term. This penalty term, as defined max of 0 or g x, is a very useful penalty term. It is mostly used to handle inequality constants. Here also we start with a small value of R and then gradually increase the value of R as iteration proceeds. Inverse penalty for inequality constants, which is defined as minus R by g of x. Here we start with a large value of R and then gradually reduce the value of R. Since all feasible points are penalized by this parameter, by this penalty term, this is known as interior penalty term. So, inverse penalty for inequality constants is an interior penalty term. So, these are the various penalty terms that you can use to form the penalty function. So, by adding these penalty terms for inequality and equality constants, you can formulate the penalty function. So, the penalty function will be formulated by adding these penalty terms to the objective function of the original nonlinear programming problem. So, that way we will get an unconstant function which can be solved for a particular value of penalty parameter r. Then you can solve the unconstant problem again by taking different value of r, and by doing so you will slowly approach the optimum of the original nonlinear programming problem. You have seen that for exterior point methods, we start with a small value of r and then gradually increase the value of the r. But in case of interior point method, we start with a larger value of r and then slowly reduce with iterations. Let us see now how this exterior penalty works. So, the penalty function will be formulated as shown. Note that I have added the parabolic penalty for the equality constants and the max operator or the bracket operator for the inequality constants. In case constants are satisfied, the g of x less or equal to 0 means the constants are satisfied. So, we are solving a minimization problem with inequality constant g of x less or equal to 0. So, in case constants are satisfied, the contribution of this bracket operator will be 0 and there will be no penalty on the objective function. In case constants are violated, that means g x greater than 0, the bracket operator will be a positive value resulting in a penalty on the objective function. The penalty will be higher for higher infeasibility of the constants. That means, the penalty will be higher when the constant violation is higher. The penalty function p can be optimized using the algorithm for unconstant problems. The penalty function method of this form is called the exterior penalty function method. Now, here look at the graph. The optimization problem that is being solved is f x equal to 2 x 1 subject to 3 minus x 1 less or equal to 0. So, the penalty function p x is the objective function plus the penalty term. So, for the penalty term, let me use the bracket operator or g of x. So, let us take different values of this r equal to r k equal to 1, 2, 3 etcetera. So, these are the sequence when you take r k or the penalty term value r equal to 1, 2 and 3, and you see how you approach the optimum point for the original problem. So, this part is infeasible, this is the feasible type, this is the feasible part and this is the infeasible region. So, as you approach the optimum, you always remain in the infeasible region, you approach the optimum from within the infeasible region. So, we start the algorithm with a small penalty parameter r and increase it to a larger value for the purpose of tightening the constants at later iterations. Now, let us look at the interior penalty. In the interior penalty function method, a feasible point is first selected. The objective function is modified in such a way that it does not leave the feasible boundary. They are therefore frequently referred to as barrier function methods. So, in case of interior penalty function method, a feasible point is first selected. The objective function is modified in such a way that it does not leave the feasible boundary. It always remains within the feasible region. These methods are therefore frequently referred to as barrier function methods. So, the modified objective function in case of interior penalty function method can be as shown. Note that I have used an inverse penalty term minus r by g by minus r by gx. So, if you have m number of constants, you have to add up 1 by g I x summed over all I equal to 1 to m. So, this way you can formulate the penalty function method while using interior penalty term. Particularly here we have used inverse penalty term. Note that this is an interior penalty. So, if you pictorially present, this is the feasible region. So, we start with a higher value of the penalty term r and then go on decreasing the value with later iterations. So, you see we always remain within the feasible region. We do not leave the feasible region and approach the solutions from within the feasible region. So, interior penalty function method approach the optimum while remaining within this feasible region method. We started with higher value of penalty term and slowly reduce the value. In case of exterior penalty function method, we approach the optimum while always remaining within the infeasible region. So, we approach the optimum from the infeasible region. And in case of exterior penalty method, we started with a smaller value of the penalty term r and increase the value of the penalty term in later iterations. What are the advantages and disadvantages of penalty function method? It can be started from an infeasible point for exterior penalty function method. The unconstant optimization methods can be directly used. As I told you, there are a host of powerful, robust, unconstant optimization methods which can be used directly to solve the nonlinear programming problem after you have converted it to an unconstant problem using penalty function method. So, conceptually the penalty function approach is extremely simple. In terms of implementation, it is also simple, and since the unconstant optimization techniques can be used, it has an advantage. There are some disadvantages also. The function becomes ill conditioned as the value of the penalty term is increased. The gradient value may become large and the algorithm may show divergence. Another disadvantage is this, that this method does not satisfy the constraints exactly. It is not suitable for optimization problems where feasibility must be ensured in all iterations. Let us consider this nonlinear programming problem. You have to minimize the function f x equal to minus x 1 x 2 subject to two inequality constants. Initial estimate is x 1 equal to 1 and x 2 equal to 5. So, how do you go about it? So, you formulate the penalty function. So, penalty function will be minus x 1 x 2 as the objective function plus these terms, that means r into g 1 x whole square plus r into g 2 x whole square. And you know g 1 x is nothing but max of 0 or g 1 x. Similarly, for g 2. So, this is an unconstant function. Now, you set r equal to 1 and solve it. So, you get x 1 and x 2 as solution for that unconstant problem. Next, you take r equal to 10, again solve, you get solution for as x 1 and x 2. You again consider r equal to 100 and again solve using numerical methods, and then you see that you are slowly approaching the optimum solution for this original constant nonlinear programming problem. With this, we stop lecture 48 here.